Hello, everyone. My name is Sajid, and I am a second-year PhD student working with Dr. Jesus Perez-Rios in the Theoretical Atomic and Molecular and Optics group. And today, I'll be presenting to you about the work that I did over the past year about quantum Monte Carlo simulations of atom-ion clusters. So in this talk, I'll first start off with an introduction of what atom-ion clusters are, and then I'll give you a description of the different numerical algorithms that I'll be using to compute their ground states. And then I'll talk to you about the two different systems that I explored, the ytterbium positive ion and the bath of lithium neutral atoms, as well as protonated argon clusters. And then I'll talk to you about the current work that I'm doing analyzing the dynamics of an ion in an ion trap. But first, I'd like to start off by defining what is an atom-ion cluster. An atom-ion cluster, for the purposes of this talk, consists of a charged atomic ion closely interacting with a bunch of neutral atoms. So I have several examples here. These two are from my own work, and they're simulation results of a green ytterbium positive ion surrounded by purple lithium atoms. The one on the far right is a protonated argon cluster where you have a proton in the center surrounded by argon atoms. And then the one on the bottom is a quantum chemistry result of the most stable geometry of another protonated argon cluster. So why are atom-ion clusters important? Well, if you study atom-ion clusters in the ultra-cold regime where you cool it down so much that the effects of temperature are almost negligible, then atom-ion clusters can give you insights into the fundamental quantum mechanical aspects of the interactions between atoms and ions. Also, atom-ion clusters are important because they feature in a lot of different kinds of processes. So for example, one theory for how clouds form is that first the sun ionizes a bunch of molecules or atoms, and then those ions attract more atoms in the atmosphere towards them, forming all these clusters. And these clusters are basically the aerosols that attract water molecules that form clouds. Another reason why atom-ion clusters are important is because they're experimentally accessible. If you want to study a bunch of clusters of just neutral atoms, those neutral clusters won't bend in the magnetic field in a mass spectrometry. But if you have charged atom clusters, then you can do a mass spec on them. Also, atom-ion clusters are important because basically, if you have a trapped ion, you can use that as a qubit for a quantum computer. And so, for example, Quantinuum is exploring trapped ion quantum computing. And the thing is that you cannot have a perfect vacuum. So if you have a trapped ion, it's not going to be on its own. There are going to be other atoms floating around nearby, and they might form atom-ion clusters. So one feature of atom-ion clusters that is prominent is something called coordination. So a coordination complex basically consists of a central ion surrounded by a geometrically symmetric array of bound atoms. And these atoms are bound to the ion not by covalent bonds, because if you look on the right, there are so many atoms surrounding the central ion that there's just not enough electrons to share. So instead, what happens is the ion electric field polarizes the atoms nearby, and those temporary polar atoms are attracted to the ion. One way of characterizing these atom-ion clusters is something called a coordination number, MC, which is the number of atoms in the first solvation cell surrounding the ion. So, for example, the coordination number for this cluster would be 12, because there are 12 atoms. And the idea is that the coordination number is something that should minimize the average ground state energy per particle. So the system that I'll be exploring in this talk is, or one of the systems is a ytterbium positive ion surrounded by a bath of lithium atoms. So we have one ion and n atoms. And so each of these atoms and ions can move in 3 different directions. And so there are 3 times n plus 1 degrees of freedom in the system. The potential energy of the interaction between each pair of atoms is modeled by this VAA of R, which is called a Leonard-Jones potential. The minus C6 over R to the 6th is due to the induced dipole interaction between the atoms. And then the interaction between the atom and the ion is modeled by the VAI of R over there, which is in the long range behaves as minus C4 over R to the 4th. due to the polarizability of the atom and the ion's electric field. And the total energy of the system is basically the kinetic energy of all the particles plus the sum over all pairs of particles of the potential energy between the particles. So the questions that I'll be exploring here are basically what kind of geometries will the atoms form when they surround the ion in the ground state? And what are the most stable atom-ion clusters that you're going to have? And how many atoms will be in the most stable structure? And what is the effect on these structure geometries? What is the effect of the atom-ion potential depth on these structure geometries? And so to answer these questions, I'll be showing you how I ran quantum Monte Carlo random number simulations for the ground states of these clusters for different numbers of atoms, up to 90 atoms. Now I'll describe how the algorithm of diffusion Monte Carlo works. So diffusion Monte Carlo can basically be derived from the Chowdhury equation, and the goal of this algorithm is to derive is to numerically calculate what is the ground state potential energy, the ground state wave function, and the ground state energy of the system. So if you start with the Chowdhury equation, where you have I times h bar times d psi dt equals Hamiltonian applied to the wave function, and you, instead of propagating the Chowdhury equation in real time, you switch to imaginary time, tau equals it, and you plug that into the equation, then the Chowdhury equation it starts to look like a diffusion equation with a source. So basically, psi is representing the probability density of some kind of substance diffusing throughout space in imaginary time, where you have this diffusion term here. And then if you switch the potential energy to be the potential energy minus some constant ground state energy, that acts as a source term for this diffusion equation. And one way of thinking about this diffusion equation is shown on this schematic diagram on the right, where on the top you have what the potential energy surface might look like. And then in this first row, you have several what are called walkers, which are different samples of the coordinates where the particles can be. And at each step of the process, they're basically doing Gaussian random walks, diffusing throughout the space. And the source term, what the source term does is if the particles are closer to the depth of the potential, the deepest part of the potential, then they're more likely to duplicate. So you can see how this walker is duplicating and forming two new ones. Whereas if the walkers go further away from the deepest part of the potential, then they're more likely to die off. And the idea is that if you repeat this process several times, eventually the walkers will distribute themselves according to the ground state wave function. And it's important to note here that it's not the square of the wave function that they're like converging to. It's the wave function itself, because of the analogy with the diffusion equation, where it's the wave function itself varying with imaginary time. So therefore, if we want to interpret psi as a probability density, we need it to be greater than 0. And so this method, as I'm going to state it now, does not apply to the case where you have identical fermions. So to solve this problem, there will be a bunch of walkers diffusing via random walk and replicating or dying depending on how close they are to the potential well. So now I'll describe the sort of in more detail what's going on. So basically, you start off with a bunch of walkers at any initial location that you want. And then for several iterations, what you do is that each walker takes a Gaussian random step, which is just like a Gaussian random number with a standard deviation proportional to 1 over the square root of the mass of the particle. And then after you move all those walkers by a little bit, they either replicate or die, depending on how far they are from the potential well. And this formula gives you basically how many walkers remain after you either replicate or kill it. And at each step of the way, you don't actually know what the initial ground state is, so you have to keep updating your guess of what the ground state is. And it turns out that it's the average over all walkers of the potential energy of the walker. One of the key steps in this algorithm is replicating or killing the walkers. And what I'm going to show here is a way of doing that in an optimal amount of time. So what I'm showing on the left is a table of the different coordinates that all these walkers can have. I have 10,000 walkers here. And some of these walkers are dead because they were like killed in the last step because they drifted too far away. And this array shows the list of indices of the dead walkers in this list. So since 9999 is dead, we have 9999, a dead index here. So if you want to, in the next step, replicate a walker, so let's say we want to replicate walker number 2. So what we do is we copy the coordinates of walker 2 onto a location in this list where one of the walkers is dead or unoccupied. And if you already know the index of where the unoccupied walker is, all you have to do is copy these coordinates into this index 9999 over here. And this is an optimization because what I originally had was, instead of storing the dead indices, I was actually going through the list, like trying to find the first available dead walker. And you could have to search through up to 10,000 of these things if you're just searching the table on the left one by one. So this optimization sort of speeds up the code by a factor of about 10,000. And then what I'm showing in this animation on the right is an example of what diffusion Monte Carlo is doing. So this is for the system of 8 argon atoms and 1 proton. And in the beginning, what's happening is the ion is finding a location in between 2 of the atoms. And that's what causes the first dip in the guess of the energy here, because the ion is bound to those atoms. And then the third atom finds the cluster, and that's what causes the third dip. And then a fourth atom finds the cluster and makes a tetrahedron, leading to the fourth dip in the energy. The thing is that this final configuration here is actually not the ground state of argon 8H+. So if I kept going with this algorithm, I may have to wait a really, really long time for it to converge to the actual ground state wave function. So instead of waiting all this time, what if there was a way I can speed up the diffusion Monte Carlo so that it gets to the ground state much more quickly? In one way is by choosing a very good initial condition for the walkers. So if the walkers start very close to the ground state, then I won't have to wait that long for diffusion Monte Carlo to converge. And one way of finding the initial condition is by using something called basin hopping, which I'll explain now.
Oh, sorry to interrupt, but you mind sharing your screen?
Sorry about that. So how does basin hopping work? Well, basically, we want to find the lowest possible value of the potential energy function. And the way we're going to do this is outlined here. So basically what I'm showing on the graph on the right is what the original potential energy surface might look like, this V of x, which is the dark curve. And we want to find the minimum of this dark curve. And there are several local minima. What we're going to do is we're going to metropolis sample, basically, but we're not going to metropolis sample the potential energy curve itself, but we're going to metropolis sample the energies that you would get if you started a local minimum optimization at a particular location. So basically, given any location x on this curve, if you start a local minimization starting over here, then it will end up over here. And the energy that you get is this, what I'm calling E tilde. So the dotted lines are showing what this new surface E tilde of x looks like, and it looks like a bunch of basins. And so we're going to metropolis sample or basically hop from basin to basin to compute the global minimum of this V of x. Explain in more detail what the global minimum is, how it's going to be obtained. Well, first I should point out that there is a certain temperature in the metropolis sampling formula, which the temperature is going to be proportional to the distance between successive local minima. And for several iterations, what we're going to do is we're going to propose, we have an initial coordinate, and then we're going to propose a trial coordinate, which is some random perturbation of your current guess. And then, given your new guess x2, you're going to calculate using gradient descent the local minimum that of the v of x that you would get if you started at x2, and that's e tilde of x. And then you're going to accept this new guess x2 with probability depending on the difference in the energies that you get from x1 versus x2. So if your x2 has a better energy, then you automatically accept it, probability 1. But if your x has a worse energy, then the probability that you accept it is going to be proportional to the exponential of the difference in the energies. And the idea is that if you repeat several iterations of this, in principle, the walkers will explore the full space of basins. And if you keep track of the minimum energy that you get, that will in principle converge to the minimum possible potential energy. So
The single line in that window? Yeah.
thank you very much. So now I'm going to describe one of the key steps of basin hopping, which is the act of calculating a local minimum. So calculating a local minimum by default, the way SciPy would do it is by sampling the potential energy function, not at just one point, but several surrounding points in order to calculate the difference between the functions in order to calculate their gradient. And since I have so many degrees of freedom, like 3 times n plus 1, where n can be up to 100, I have like 300 degrees of freedom. And so calculating a local minimum might require me to calculate v of x several hundreds of times. But instead, you can avoid this costly procedure by giving the algorithm an analytic form for what the gradient should be. So if I have these potential energy functions, they happen to be mathematically simple, and so I happen to know already what an analytical formula for what the gradient should be. And if I plug this formula for the gradient into this Jacobian parameter of the minimized function, this Jacobian just means gradient. I plug this method into the gradient, then the minimize will just automatically evaluate this function and it won't have to do all the finite differences. And when I empirically tried this, I found that this makes the code run 10 times faster. So I've described diffusion Monte Carlo for calculating the ground state, and I've described the basin hopping that sort of accelerates that process. And now I'll talk about one more optimization that takes advantage of the fact that we can parallelize over several cores. So on the C-Wolf clusters, we have several of these nodes, and on each of these nodes, there are like up to 96 cores, and you can run tasks independently on each core, all tasks at the same time. And it's good for me to take advantage of this because I have several tasks that I want to run. I have to run diffusion Monte Carlo for several different numbers of particles, and I have to run it several times in order to minimize the statistical uncertainty. And I happen to know roughly the runtime of the diffusion Monte Carlo algorithm. It's on the order of n squared because the potential energy function basically scales quadratically with the number of particles because it's the potential energy for each pair of particles. And the number of pairs of particles is n squared. So basically I have a bunch of tasks and I know how long they're going to run. So the question is, how do I best distribute these tasks across the different cores in order to minimize the amount of time that it takes for the whole thing to finish? And one algorithm that's sort of answered the question heuristically is the longest processing time algorithm. And the idea here is to always schedule the longest remaining task to the first available core. And so to explain what that sentence means, longest available task to first available core, I'm going to show an example here. So suppose, for simplicity, that we have only 2 cores, and we want to run tasks that we know are going to take 1, 4, 9, 16, 25, 36, and 45 minutes. So we want to distribute these tasks to the 2 cores, and one non-optimal way of scheduling them is to take task 1 and give it to core 1, give 4 to core 2, 9 to core 1, 16 to core 2, and just alternate like that. And in this case, core 1 takes 84 minutes to finish, while core 2 takes 56 minutes to finish. And if both of the cores start at the same time, then the overall amount of time you have to wait is 84 minutes. But you can do slightly better than this. You can use the longest processing time algorithm to schedule the longest remaining task to the first available core. So in the beginning, the longest task takes 49 minutes, so you schedule that to core 1. And then the longest remaining task is 36 minutes, and you schedule that to core number 2. And then, since core 1, 49 minutes takes longer than core 2, 36 minutes, core 2 is going to finish the 36 first, and so you schedule the 25-minute task to core 2 as soon as it finishes. And one more example, if 36 plus 25 is 61 minutes, and 49 is less than 61. So the 49 will finish before the 36 plus 25 finishes, and so you schedule 16 to core 1 as soon as it finishes, and so on. So in this case, core 1 and core 2 take almost the same amount of time, 69 and 71 minutes, and you have to wait 71 minutes for it to finish. And it might seem like 84 minutes and 71 minutes are not that much different from each other, but the diffusion Monte Carlo takes much longer than this number of minutes to run for a large number of particles. Take, in fact, up to 7 days to run. And so 84 versus 71 can mean the difference between like 7 days versus 6 days. Like I can save an entire day with this algorithm. And it's worth pointing out that the longest processing time algorithm is actually not the optimal for any given problem, because even in this problem, for example, there is a way of scheduling the tasks so that they both cores take exactly 70 minutes to finish. And there isn't really much of a difference between 71 minutes and 70 minutes. And it turns out that you can mathematically prove that the longest processing time algorithm is at worst takes 4/3 times as long, or 33% longer than the optimal solution for any instance of this problem. And so that's what I use to optimize this. And now I'm going to talk about the system that I'll be exploring and the results that I found. So just as a reminder, the system I'm exploring is a ytterbium positive ion surrounded by a bath of neutral lithium atoms. And I'll be exploring basically what are the ground state geometries for different numbers of atoms. And the results of that are shown here. So there's a lot to unpack in this plot. And basically what I'm doing is on the x-axis, I have the number of particles. And on the y-axis, I have the total ground state energy averaged, like divided by the number of particles. And in the beginning, for small numbers of particles, each additional atom that you add is going to decrease the energy rapidly. And this is because the atoms are accumulating right next to the ion, where the atom-ion potential is very deep. And so that decreases the energy very rapidly. But at some point, you reach a point where the more atoms you add, at some point, there's not enough room on the first shell surrounding the ion to fit additional atoms. And so the atoms accumulate further away. And the atoms accumulating further away are further from the ion and less deeply bound to the ion. And so the energy does not continue to go down. It sort of goes up and becomes asymptotic. And now most of the energy is coming from the atom-atom interaction. I have 4 different curves here because I'm showing 4 different atom-ion potential energies. All these atom-ion potential energies, these 4 of them, have the same long-range behavior coming from the polarizability of the atom, C4 over R to the 4th. But they all have different C8s, and the idea here is to explore the effect of the short-range portion of the interaction on this behavior. In particular, the yellow and green curves show the realistic atom-ion potential depth that you would get for the triplet state of the electrons and an average over the triplet and single states of the electrons. So for the yellow curve, I find that this most stable structure has an ion surrounded by 8 atoms, and they form sort of this cube where it's not really a cube, but it's the top face is rotated by 45 degrees. And the green curves has the most stable structure showing an ion surrounded by 9 atoms. And just to explore the effect of the atom ion depth further, I tried one that's even deeper and one that's even shallower. And so for the deeper one, I find that less atoms are attracted to the ion and they form an octahedral shape. And for the blue curve, the atoms form an icosahedron surrounding the ion. An icosahedron is basically a very symmetric 12 vertex geometric figure. And to explore the effect of the depth on the number of atoms in the most stable configuration a little bit further, I found that if you plot the number of atoms versus the depth, they have a very nice relationship. So basically, the number of atoms is proportional to 1 over the square root of the atom ion potential depth. And this relationship is sort of an artifact of the potential energy function that I'm using. And I'll explain that now. So basically, the atoms on the first shell around the ion, the atoms distribute themselves evenly over a sphere of radius RE, where RE is the distance that minimizes the atom ion potential energy. The atoms, when they distribute, the atoms themselves space themselves out in order to minimize the atom-atom potential energy. But the atom-atom potential energy is being kept fixed here. So this equilibrium distance, which is proportional to the 4th root of C8 on the one hand, and the potential depth, which is proportional to 1 over C8 on the other hand, can be used to derive the fact that the number of atoms in the first shell, which should be proportional to the surface area of that sphere, is proportional to 1 over the square root of the atom ion potential depth. And on this slide, I'm showing the probability densities for where the atom can be with respect to the ion. So on the top, it's a probability density of the atom ion distance. And the dotted lines are showing the equilibrium distances of the atom ion potential. And what's happening here is that the first peak is to the right of the dotted line, which means that the most likely, or the average atom ion distance, is typically on average greater than the atom ion equilibrium distance. And so what's happening here is that there are two forces competing with each other. The ion is attracting the atoms to it, which is squeezing them together. But the atoms are being squeezed so close together that they're repelling each other. So the ion, and so that's why the atoms are further, not so close to the ion, because the atoms are repelling each other. And on the bottom half, I'm showing, so this U of R just means what is the probability density for the atom-atom distance. So I basically sampled all the atom-atom distances and made a histogram of it, basically. And the dotted line on each of these is the atom-atom equilibrium distance, potential distance. And the first peak on each of these curves is typically to the left of the dotted line. And what this means is that the atoms are being dragged closer, so close together, that the atoms are typically closer to each other than they would typically be if the ion was not present. And so what this means is that the ion is electrostricting the atoms. And so this is displaying the phenomenon of electrostriction. On this plot, I tried yet another atom ion potential depth for the purple and blue curves. The long range of these blue and purple curves is still going to be minus the same C4 over R to the 4th, but I have different C8s here. And for the purple curve, it's slightly deeper, still slightly deeper than the atom-atom potential energies shown by the black line. And for the purple curve, the most stable atom-ion cluster is still an ion in the middle surrounded by several shells of atoms. And then if you have the atom-ion potential more shallow than the atom-atom potential, it turns out that it's more energetically favorable for the ion to be outside of the atom cluster. And this can be like in retrospect, I realized that since the atom-atom potential energy is deeper than the blue curve here, it's more energetically favorable for the atoms to be closer together. Whereas if the ion was in the middle of the whole thing, you would be preventing a lot of the atoms from being as close to each other as they want to be. And so what I'm basically predicting here is that if the atom-ion potential energy is shallower than the atom-atom potential energy, then in this case, for example, the ion might prefer to not dissolve in the bath of lithium atoms. This plot over here is just showing the probability density for the atom-ion distance for each of these two clusters. So for the first cluster, since the ion is in the center, the atoms are forming different shells around the ion, and so these peaks correspond to the different radii of the shells that their atoms are forming. Whereas the one on the right has an atom cluster with an ion on the outside, and the peaks in the atom-ion distances are basically more spread out, simply because the atoms have several different distances from the ion on the outside. So now I'll talk to you about a very similar system, which is a protonated argon cluster. So a protonated argon cluster is mathematically rather similar to the ytterbium lithium case. So all I did was change the ion, change the atom, and there are new interactions between them. In this case, the ion is very light. It's a proton, and the atoms are much heavier than this proton. And the atom-atom interaction is still being modeled by a Leonard-Jones potential with the different C6 and C12. And the atom-ion interaction from the reference that I had was computed in a slightly more complicated way in the short range, but still in the long range, the atoms are polarized by the ion electric field, and so it still behaves as minus C4 over R to the fourth in the long range. And the total energy is still the kinetic energy plus the sum of the potential energies. And so since this system is so much similar to the previous system, I can again use diffusion Monte Carlo to figure out the most stable cluster sizes and geometries and the binding energies. And binding energy in particular, so we want to find how stable are these clusters in terms of the energy cost it takes to remove an atom. So the binding energy of argon H plus is the ground state energy of argon H and H plus minus the ground state energy of argon N minus 1 H plus. And so this energy, if it's really large and negative, it means that it costs a lot of energy to remove an atom from this cluster, which means that the cluster is more stable. And so I wanted to explore what these binding energies look like. And so this plot shows the results of the diffusion Monte Carlo calculations. So we have on the x-axis the number of atoms in the cluster, and on the left y-axis we have the binding energy of n minus energy with n minus 1 particles for atoms. And the y-axis on the left corresponds to the black and red points, the red points being the basin hopping results and the black points being the diffusion Monte Carlo results for the energy. And then for the y-axis on the right, basically they did an experiment where they have a bunch of argon atoms and they injected protons into it, and then they did a mass spectrometry of the different argon and H plus clusters that you can get. And so these purple dots are showing the most often, like basically the yield of each of the atom ion clusters that they got in their mass spectrometry. And the peaks in the yield that they got, the red ones in particular, or the red lines, align very closely to the deepest parts of the diffusion Monte Carlo energies that I obtained in my calculations. So this agreement between experiment and theory can be explained by the fact that the most stable clusters are the ones that are the most likely to be found if you wait for them to interact and exchange atoms with each other and so on. It's basically like survival of the fittest. So for example, the deepest bound structure here is with 26 atoms. And so this E of n minus E of n minus 1 is very large and negative, which means that it costs a lot of energy to remove an atom from that cluster. And so if that cluster is formed, it's going to stay like that in a more stable configuration. And so these stable configurations are the ones that are being most likely to be found. And on the next slide, I'm going to show the geometries of what these configurations look like. So here is a diagram from the simulation software I was using of the different positions of the atoms in these clusters. So the one on the top left is you have one proton in the center, the gray thing, surrounded by 19 argon atoms. And this structure has like a five-fold rotational symmetry because you can see there's like a pentagon, pentagon, pentagon. So you can rotate it. And the other clusters do not, it's kind of hard to describe what these things are geometrically. But the one on the bottom right, the cluster on the bottom right is 55 atoms. And the cluster with the 55 atoms is actually, the ion is sort of not in the center. There's actually an atom in the center. And I'll show in more detail what this cluster looks like. So here we have, it's rotating around the center of mass. And so the atom, one of the argon atoms is in the center. The ion is off to the side. And then you have an icosahedral shell. So one atom surrounded by a shell of 12 argon atoms, surrounded by another icosahedral shell of 42 atoms. And you can see how the atoms sort of form like this like crystal structure because they're all, if you line it up in a certain way, they're all lined up. And one of the things I wanted to explain was why these binding energies of these clusters are sort of hovering around 800 Kelvin of energy. And one way to see this is that each additional atom that you add typically has 6 nearest neighbor atoms that it goes near. So for example, for this 55 argon cluster, this top atom has 6 nearest neighbors. And most of the energy that top atom contributes is coming from the interaction with its nearest neighbors. And it turns out that this atom-atom interaction for each of these pairs of atoms is 142 Kelvin of binding energy. And so the 6 times 142 is 150 Kelvin. And you also have to account for the fact that there's like 0-point kinetic energy. And so that explains why this thing is hovering around 800 Kelvin. And it's not like asymptotic to 800 Kelvin. It's going up and then down and then up and then down. And the reason is that if you add an atom to a cluster, it's not just like, you don't just add an atom and that's the new geometry. Each geometry is completely different from the previous one, typically. So when you have 40 atoms, that makes one geometry, and that has a certain ground state energy. But then if you add another atom, the 41 atoms can have a completely different geometry in the ground state. And this different geometry is going to have a different number of nearest neighbor atom-atom and atom-ion pairs. And so that's why this graph is going up and down and up and down. And finally, I'll look into the current work that I'm doing with the dynamics of an ion in a multipolar trap. So far, in all this work, I haven't considered the effect of the trap. Actually, I have, but it turns out that if you model the ion as being trapped in a harmonic well, then the trap energy does not affect the binding energy of the clusters very much. However, if you have an ion and an atom interacting with each other dynamically, the dynamics of the interaction is affected by the multipolar trap here. So one way of trapping an ion, so this work is like almost completely different from the previous slides that I've been doing. This is almost completely different. You have an ion in the center of what's called a multipolar trap, which consists of electric fields that are sort of oscillating. So you have like this kind of electric field potential energy, and that electric field is oscillating, and that's what's trapping the ion. And what I'm going to show you is my simulation of, depending on where you start the atom on this sphere, if you launch an atom from the boundary of the sphere directly towards the ion, how long will the atom and ion interact with each other before the atom leaves? And so this is what it looks like. You have, on the x-axis, you have the theta, which is the initial spherical theta angle where I'm launching the atom. And then on the y-axis, you have the initial spherical phi angle. And the color is showing the number of times that when the atom goes to the ion, how many times does this trajectory sort of bounce? So this is a classical molecular dynamic simulation. I'm just counting how many times the atom bounces before it leaves again. And so what this is showing is that there are certain specific angles, like theta equals pi over 4 and 3 pi over 4, and certain angles of phi, where the atom and ion are much more likely to stay orbiting around each other for a much longer amount of time. And this can be explained by the asymmetry in the ion trap. And then there are some regions here that appear very they have a very intricate structure to them. And perhaps if I zoomed in to like this central ring here, I might find even more rings. And so one thing that I'll be exploring in the near future is if we interpret this thing as a kind of fractal or something that has a very intricate structure, then what is the fractal dimension of this thing? And something I can do is I can use the box counting method to calculate the fractal dimension. And so now I'll conclude what I've done. So in conclusion, I found that diffusion Monte Carlo, if you augment it with basin hopping and the longest processing time algorithm, diffusion Monte Carlo becomes a very powerful and general algorithm for finding the ground state for many kinds of quantum systems. The diffusion Monte Carlo calculations of ytterbium ion in a bath of lithium atoms shows geometries that you can probe experimentally. And in the case of protonated argon clusters, my DMC calculations show very close agreement with the experimentally determined stable atom ion clusters. And then I'll be exploring the chaotic dynamics of an ion interacting with these atoms in the future. And so I'd like to end the talk by thanking my advisor, Dr. Jesus Perez-Rios, who is not here because he's giving another talk right now, as well as my other group members, and they're very fun to work with. And also, thank you for listening to my talk. Questions?
Why do you use more potential for the closer end of argon photon?
So depending on, basically I took there's this reference here where they carefully calculate what the potential energy surface should be. And in this case, they found that it was closely modeled by a Morse potential in the short range.
So, maybe I missed it slightly, but a Walker is behavior of a single atom. Or is it the behavior of the whole system at time?
So Walker is the behavior of the whole system. So basically a Walker is the set of coordinates that all the atoms and ion are occupying. It's a sampling of a multi-dimensional vector, and yeah.
So as a follow-up to that, when you calculate the different energy bases, so your calculation for simplifying the Monte Carlo steps is to calculate the behavior would be through all the possible big basic minimum energy configurations. Is that right? So what does each basin calculating for each basin mean basically?
So each basin is a local minimum of the potential energy curve. So if you have like this sort of semi-stable structure with the octahedron and atoms sort of in other locations, that's a local minimum of the potential energy. So that's what these basins represent. So the lowest basin is going to be the global minimum.
Yeah, so I'm curious, it was really interesting seeing how changing the parameters of the model changed the structure. Presumably you could separate the depth and the distance by varying C4 and C8 separately. I wonder if you've tried that or thought about trying that.
So I've
Then you
thought
get
of trying, sorry, so it turns out that typically, if you look at real atom potentials, typically the equilibrium distance and depth both change with each other. They are related to each other. But if you had like a C6 coefficient in addition, then maybe you could change both of them. I didn't really look into that.
Thanks.
Yep.
You talked about how some configurations, like the final state will end up is with the ion outside or outside of everything.
Mhm.
I guess like what kind of initial conditions do you find that those systems get into that final state? Sorry.
I've tried two different kinds of initial conditions. So the basin hopping initial condition, it turns out that the global minimum of the potential energy also looks a lot like this. I also tried random initial conditions without the basin hopping, where the ion is sort of spawned in a random location in some sphere, and all the atoms are also spawned in random locations. And usually I found that it still converges to this thing where the ion goes to the outside. There were some cases where when the ion was like in the middle of the whole thing, it didn't
Like break out or
it didn't break out in time. But those energies, when the ion was inside, were still not as deep as the energies when the ion is outside.
Can you go to the density profiles? Any of the density profile? Yeah, for example.
This one,
Yeah. The purple one has like if you show me this density profile without the picture of the cluster, I would think like I have the atom and I have a spherical shell and then another spherical shell with a little bit of deviation, but I see a very disordered like configuration, or maybe I know seeing very well how this configuration looks like, but you have two peaks, right?
Yeah.
A peaks distant r. What that means, like, it's a sphere. For me, it's a sphere, right? Because you have the center, you have the distance, it's a sphere, and then you have one more sphere with a larger radius. Why doesn't that look like a sphere?
it's because the first peak here is it's hard to see from here, but there's like an octahedron of atoms surrounding the ion, and that octahedron is very symmetric for the first one. For the second one, it's hard to see, and then the third one, I may have renormalized this the wrong way, to be honest with you, but there are multiple peaks here. It's not just
Okay,
one peak like this.
makes more sense. The other thing is, this is like a static picture, like an average on some oscillation modes of the cluster, because I mean, the cluster is not static.
Mhm.
Right? Like, you have any idea if the cluster have like a specific oscillation mode, so where is the motion of the cluster? You know, they should have some.
Of course they should. So the thing with the diffusion Monte Carlo is that it cannot tell you anything about the real dynamics of the system. The whole thing is propagated in imaginary time, and all it can give you is what the ground state is. It cannot give you, so for example, these oscillations here, when they do their random walks, these oscillations are in imaginary time. These are not the actual oscillations. So really, this method cannot tell you what the frequencies are going to be.
So, thanks, very good.
Any other questions or comments? Yep.
So when when you do the diffusion Monte Carlo, and then you have the time steps, like, do you move like, it's basically a follow-up from the question, but do you move only like one atom or do you move all of them?
So since a walker consists of the coordinates of all of them, I move all of them in one time step.
Okay, so you displace all of the coordinates a little bit, or like,
So what I do
I'm
is
just interested in the details, or
Yeah, of course.
how you decide to move from one time step to the next.
So what I do is I take a Gaussian bell curve with standard deviation given by this formula, and I just sample that bell curve. And that gives me the amount by which I nudge a particular coordinate. And so for the ion.
Oh, and you do that for each, like for X, Y, and Z of each atom.
Exactly, for each direction, yeah. The derivation for that is a little bit complicated, like the fact that this works, you could use like the path integral formulation to derive it, but maybe I shouldn't go into that. Yep.
So you kill and replicate walkers, is like the way you decide that, the number of walkers big, or in that fluctuate?
It's a good question. So it does fluctuate. There's a 3 in that formula there, which means that you can't generate more than 3 walkers. And so if I start with 10,000 walkers, I can't end up with like 30,000 walkers in the end. And typically it does fluctuate around, it's like if I start with 10,000, it fluctuates around like 9,000-ish.
So when when a walker died, like does it mean the coordinates don't exist or whatever? Like
It means you delete the coordinates from this list, like that walker is not part of the distribution anymore.
you know what temperature the experiment happens.
I do not remember, but if you look at the citation, it'll tell you.
Do you keep a list of the coordinates of the dead walkers?
Yes, so. I do not keep the coordinates, I only keep the indices, because I don't need the coordinates anymore.
No, the coordinates, just because you could accidentally start in the same spot.
Yeah, so so in this list, instead of having the original coordinates, I just ignore them. And whenever I copy over, it's like, it's being copied over, so like it overwrites whatever coordinate used to be listed there. So at each iteration, we actually go through every single walker individually. And so each walker, depending on where its new potential energy is, for each one, I decide how many of them to keep. And if I need to keep 2 or more, then I copy it. If I need to keep 1, then I don't do anything because the 1 is already there. And if I want to keep 0 of them, depending on this formula, if this formula gives 0, that means I'm going to kill the walker. And I go through the entire list of live walkers to determine how many to keep.
What is the coordinates of this again representing? You talked about how like the walker represents an entire configuration. So what is, I guess, the coordinates in like an X, Y, and Z in what, like the ion position?
Oh, so these coordinates are just like a dummy example because you can't
okay.
list all the coordinates that they
Yeah,
have.
yeah.
So typically, if I have n atoms and 1 ion, there's going to be 3 times n plus 1 coordinates listed out for each walker.
I guess I'm trying to piece the things together. Part of it is because I actually missed the introduction. So you're using diffusion Monte Carlo to get the next state. So you're trying to find the least energetic state of your system, right?
Essentially.
And you're using diffusion Monte Carlo to get the next state. So where does the Basin hopping come into play? So is it just like the accepting or not the new state?
So
Is it like, is it a combination? I guess that's my question. Do you use it combined with Diffusion Monte Carlo or?
I do
are they
not.
separate?
So it's like a 2-step process. First, I do the Basin hopping to get the global minimum of the potential energy. And then from that, that's the positions of the particles that minimize the potential energy. Those positions are used as the starting positions for the diffusion Monte Carlo. And diffusion Monte Carlo runs completely separately after Basin hopping finishes.
So it like improves it, it like finesses it or something?
Finesses it in the sense that instead of this curve starting all the way at the top, the curve would start much closer to the bottom,
Okay,
much closer to the global minimum.
I see. So first Hawking, then diffusion.
I guess if there are no other questions, thank you very much.